Hello, I'm Hyungju Kim, an associate professor at the Department of Maritime Operations at the University of Southeastern Norway. This video is a tutorial for the Systems Theoretic Process Analysis, STPA. This tutorial is based on STPA handbook written by Professor Nancy Leveson and Dr. John Thomas. And you can freely download this handbook from the link here. And based on this handbook, we will use a firefighting system of a vessel as a study case. So as you can see from the figure here, we have a very large engine for a large scale ships like this. And sometimes these engines are very large like this, like 4 or 5 stories high. So for those large engines, and if we have a fire, then the fire can also be in a very large scale. So we need a very strong and effective firefighting system for the engine room for those large scale ships. And one of the most widely used system is a CO2 firefighting system. So let me give you a description of the system. So we have CO2 bottles, and these CO2 bottles are connected to the engine room by pipelines like this. And we have a master valve to control the flow of this CO2 gas. And we have a CO2 release control system and some fire detectors and CO2 release alarm. And finally, we have a human operator. And let me explain you the working principle of this system. So when we have a fire inside the engine room, then the fire detector gives some signal to the CO2 release control system that we have a fire. Then the human operator can identify the occurrence of the fire either from this CO2 release control system or directly from the engine room. So once the human operator identifies the occurrence of the fire, then the human operator initiate the releasing CO2 into the engine room. But this CO2 is a very strong and effective method to extinguish the fire, but at the same time, it is very dangerous to the human. So if there is anyone inside this engine room when the CO2 is released, then they will definitely die. So when the human operator initiates the releasing the CO2 into the engine room, then the CO2 release control system, the first activate a CO2 release alarm inside the engine room. Then this alarm provides the both visual and audio alarm. So the engineers or crew members inside the engine room, so they can evacuate from the engine room. And after a certain amount of time delay, then the CO2 control system opens this master valve. Then the CO2 flows from the CO2 bottle through the master valve to the engine room. Then we can finally extinguish the fire from the engine room. So we will use this system as our study case, and let's conduct STPA together. STPA consists of 4 steps. The first step is to define purpose of the analysis. And the second step is to model the control structure. And the third step is to identify unsafe control actions. And the last step is to identify loss scenarios. So let's follow the steps one by one. The first step is to define purpose of the analysis. So the first, we need to identify losses. And a loss is defined like this in the STPA. a loss involves something of value to stakeholders. The losses may include a loss of human life or human injury, property damage, environmental pollution, loss of mission, loss of reputation, loss or leak of sensitive information, or any other loss that is unacceptable to the stakeholder. So let's try to identify possible losses of our CO2 firefighting system. One possible loss is the loss of lives or injuries. So for instance, if we have a CO2 release inside the engine room, when we have some people inside there, then we will lose some human lives. So that can be one possible loss. Another loss can be a property damage. So for instance, if we cannot use this CO2 system, so in other words, if the CO2 system fails to extinguish the fire, then we will have a huge amount of ship damage. So this property damage can also be another loss. And we can also think about this environmental pollution. Because, for instance, if the CO2 is released when we don't have any fire, then it means that this CO2 will be released to the environment. And as you know, the CO2 is a critical greenhouse gas. So it can cause some environmental pollution. So these three are the possible losses. And the next step is to eliminate less critical or less important losses. So in this case, let's say that environmental pollution can be a possible loss, but it can be very minor. So we can eliminate this from our loss list. So this is a procedure to something like defining the scope of our analysis. So as you can see here, we will focus on the loss of human lives and injuries and the property damages. And we will not consider the environmental pollution in this analysis. So once we have identified those losses, then we need to identify system level hazard. And hazard is defined like this in STPA. A hazard is a system state or set of conditions that, together with a particular set of worst case environmental conditions, will lead to a loss. And these are important tips to prevent common mistakes when identifying hazards. So please stop this video and read through these tips in detail. Okay, then based on this definition and these tips, we will identify system level hazard of our CO2 firefighting system. So this is the overview of the CO2 firefighting system. And we have identified two losses like this. And one possible hazard is like this. Hazard number one is that CO2 is released when people are inside the engine room. And this hazard is connected to the loss number one, loss of human lives or injuries. And there is another hazard. Hazard number two is that CO2 is not released when a fire occurs in engine room. In this case, we cannot extinguish the fire. So it means that we cannot control the fire. So the people on board can die or the vessel can have serious damage. So this hazard number two is connected to loss number one and loss number two. And when we have identified these system level hazards, then the next step is to define system level constraint. And system level constraint is defined like this. A system level constraint specifies system conditions or behaviors that need to be satisfied to prevent hazards and prevent losses. So this is an example of a system level constraint in our study case. So previously, we have identified two system level hazards. The first hazard was that CO2 is released when the people are inside the engine room. An associated system level constraint is CO2 must never be released when people are inside the engine room. And the second hazard was CO2 is not released when a fire occurs in engine room. An associated system level constraint is that CO2 must be released when a fire occurs in engine room, of course, after the time delay. So this was the first step, defining the purpose of the analysis. And the next step is to model the control structure. And this is one of the most important steps in the STPA. And the control structure is defined like this in STPA. A hierarchical control structure is a system model that is composed of feedback control loops. So an effective control structure will enforce constraints on the behavior of overall system. And this control structure looks like this. This is the simplest control structure. So you can see we have one controller and one controlled process. And inside the controller, we have a control algorithm and the process model. And the controller provides some control actions to the controlled process. And the controlled process provides feedback to the controller. And of course, we may have many different shapes of the control structure. So for instance, we can have multiple controllers, or we can have some hierarchy of the controllers, or we can have 3 or more controllers with very complex interactions like this. And these are the tips to prevent common mistakes when we establish our control structure. So these are also very important. So please stop the video and read through all the details of these tips. Okay, then based on this definition here and based on these tips here, let's establish our own control structure for the CO2 firefighting system. As you can see here, we start from the CO2 bottles. We have CO2 bottles and we have engine room. And between them, we have a master valve module. And this master valve module is controlled by the CO2 release control system. And a fire detector and an alarm is connected to this CO2 release control system. And finally, we have a human operator. And when we have a fire inside the engine room, then from this engine room, we will have a smoke or flame or heat to the fire detector. Then the fire detector provides information that we have a fire inside the engine room. Then the CO2 release control system receives this information and forward this information to the human operator. Or the human operator can also directly get information from the fire detector that we have a fire. Then human operator initiate releasing CO2 into the engine room. Then do you remember that the CO2 control system does not open the valve immediately, but instead activate an alarm first. So activate CO2 release alarm inside the engine room. Then this alarm provides both sound and visual alarm. And after a certain amount of time delay, then the CO2 release control system open the master valve. Then the CO2 flows from the CO2 bottle through the master valve module to the engine room. Then the master valve module provides the valve position as a feedback to this control command. And this CO2 release control system provides CO2 release status as a feedback to this control command. And in this structure, you can see the black arrows means control command or control action, and the blue arrows means feedback, and the green ones are controlled process. So this is the control structure of the CO2 firefighting system. And once we have established this control structure, then we should identify some responsibilities and process models and the feedbacks of each controller. So in our system, we have two controllers. The first one is a human controller, and the second one is the CO2 release control system. And for the human operator, the main responsibility is to initiate CO2 release when we have a fire inside the engine room. And the process model, it's like a condition of this responsibility, is that occurrence of a fire in the engine room. And the feedback that the human operator can make a decision is a fire alarm from the fire detectors. And we can also identify the responsibilities and process models and feedbacks of this CO2 release control system. So one important responsibility of this CO2 release control system is, as you can see here, apply the time delay before releasing the CO2. And relevant process model is that CO2 release is requested by the human operator, and the feedback is CO2 release command from the human operator. And another responsibility is to release CO2 when requested by the human operator, and of course, after the time delay. For this responsibility, the process model is the CO2 release is requested by the human operator, and the time delay has been applied. And the relevant feedbacks are the CO2 release command and the time delay. This is the control structure and the responsibilities, process models, and feedbacks of our CO2 firefighting system. And the next step is to identify unsafe control actions. So to identify this unsafe control action, we will use our control structure. So let's look into the details of this definition of the unsafe control action first. So as you can see here, unsafe control action, or UCA, is a control action that in a particular context and worst case environment will lead to a hazard. And these are the tips to prevent common mistakes when we identify unsafe control actions. So please stop the video again and read all the details of these tips. Okay, then based on the definition of unsafe control action and based on these tips here, let's try to find our unsafe control action in the CO2 firefighting system. So we will use this control structure here. And we will use each of these control actions here to find the unsafe control action. So I will give an example using this control action here. Open the master valve. Then we can use this table to identify unsafe control actions. So in this table, you can see here we have an information about the controller. The controller of this control action is CO2 release control system. And we will check this control action, open the master valve. And these are conditions, and this is a process model we have identified in the step 2. So do you remember that there were two process models in this CO2 release control system? One was that human operator, request releasing CO2. Another process model was that time delay has been applied. So this is used as a condition here. So the first condition here is that whether the CO2 release command is provided from the human operator. Another condition is whether the time delay has been applied or not. So using these two conditions, and we can make 4 combinations like this. So the first condition is that CO2 release command is provided from the human operator, yes, but the time delay has not been applied yet, means that it is before the time delay. So in this condition, if this control action, open the valve, is not provided, then this is safe because the time delay has not been applied yet. But in the same condition, this control action, open the valve, is provided, then this is unsafe because the time delay has not been applied yet. So the people inside the engine room can die. So this is an unsafe control action, and this unsafe control action can be connected to the hazard number 1. Do you remember this hazard? That CO2 is released when the people are inside the engine room. And too early or too late, too short, does not matter. If it is provided, then it is unsafe. And we can check the second combination of the conditions. The CO2 release command is provided by the human operator, and the time delay has been applied. So this is after the time delay. In this condition, if this open valve command is not provided, then this is unsafe because it is after the time delay and the human operator requests releasing CO2. And if the valve is not opened, then of course this is unsafe because we cannot extinguish the fire. So this is an unsafe control action, and it can be connected to the hazard number 2. And in the same condition, if this open valve command is provided, then it is of course safe. But even the control action is provided, if it is provided too early, then it can be unsafe because the people inside the engine room may not evacuate from the engine room. Or if it is provided too late, then maybe we cannot extinguish the fire. Or too short, we cannot extinguish the fire. Too long does not matter. So we can check all these combinations of conditions, and we can check whether each control action is safe or unsafe. Then we can identify every unsafe control action from this open master valve command. Then of course, you need to check the other control action, release CO2 into engine room. So if you check all these control actions, then you can identify all unsafe control actions from your system. So once you have identified all those control actions, then you need to make a sentence for each of these unsafe control actions. So I will give you an example using this case. CO2 release command is provided, time delay, after the time delay, open master valve is not provided. Then we can make a sentence like this. This is the numbering of the unsafe control actions. Unsafe control action, release control system, number 002. So CO2 release control system does not provide open master valve command when human operator provides CO2 release CO2 into engine room command and after a delay. This is an example how to make a sentence on this unsafe control action. And it is important to include every required information when you make a sentence like this. For instance, here in this unsafe control action, you can find that we have a source. The source means that the controller that provides this control action. So in this case, the source is CO2 release control system. And the type of the unsafe control action does not provide in this case, or it can be provide or provide too late or too early and so on. And the next is the control action. Open the master valve. And the next is the context or the combination of the conditions. So when the human operator provides release CO2 into engine room command and after a delay. And lastly, you need to write the link to the hazard. So which hazard is connected to this unsafe control action? So you need to write every unsafe control action into a sentence like this. And this is the step 3. And the last step is to identify loss scenarios. And a loss scenario is defined like this. A loss scenario describes the causal factors that can lead to the unsafe control actions and to hazards. And there are 2 types of loss scenarios. One is to answering this question, why would unsafe control actions occur? Another one is to answer this question, why would control actions be improperly executed or not executed? So let's see one by one in detail. The first is this part. Why would unsafe control actions occur? So in other words, the scenarios that lead to unsafe control actions. And in order to identify these scenarios, then we need to focus on the controllers and the sensors and the feedbacks. And in this handbook, they provide some representative cases. So we can use those cases to identify those scenarios. The one representative case is failures related to the controller. So for physical controllers, like physical failure of the controller itself, or the power supply failure, and so on. So let me give you an example in our CO2 firefighting system. We have identified this unsafe control action in the previous step. So it was that the CO2 release control system does not provide open master valve command, and blah, blah, blah. And we can identify why these unsafe control actions occur using this case here. So for instance, we can use this one, physical failure of the controller itself. Then we can develop a loss scenario like this. This is loss scenario that CO2 release control system physically fails when a fire occurs in engine room. So as a result, open master valve command is not provided and the CO2 system fails to extinguish the fire. Or we can use this second case here, power supply failure. Then we can develop another loss scenarios that the electrical power is not supplied for the CO2 release control system when a fire occurs in engine room. So as a result, we cannot extinguish the fire. And the handbook provides several more cases like inadequate control algorithms or unsafe control input or inadequate process models. So you should follow every case and try to identify loss scenarios associated with each case. So let me give you another example using this case. Controller does not receive feedback or information when needed. Using this case, we can develop this loss scenario, like CO2 release control system does not release CO2 into engine room command from human operator due to a failure of a communication cable. So as a result, the system cannot extinguish the fire. So you can make these kind of loss scenarios using all these other cases. And of course, this is a very generic and representative case. So there can be many additional cases in your own system. So of course, first you need to follow all these representative cases. And after that, you need to try to find additional cases and additional scenarios. And the second types of loss scenarios are to answer this question. Why would control actions be improperly executed or not executed? In other words, the scenarios in which control actions are improperly executed or not executed. To identify those scenarios, we need to focus on the actuators and control actions and control the process. And of course, this handbook provides several cases, so we can use them as the starting point. So for instance, for the control action not executed or control action improperly executed. So let me give you an example using this case. Control action is sent by controller, but not received by the actuator. So we can use this case and develop a loss scenario like this. CO2 release control system provides open master valve command, but it is not received by the valve module due to a failure of a communication cable. As a result, the system fails to extinguish the fire. So you can develop these kind of scenarios using all the other cases. And again, you need to try to find additional scenarios because these are very generic and representative cases. So try to find as many loss scenarios as possible. That is the last step of STPA. So normally, when we conduct the STPA analysis, we will have a large number of unsafe control actions and loss scenarios. For instance, when I analyzed a subsea gas compression system using STPA, I found 130 unsafe control actions and 976 loss scenarios. Even it was a very high-level analysis, and I didn't include any details in the analysis. But still, I could have found a large number of uses and loss scenarios. And for the autonomous ships, depending on the control system type, I could identify between 80 to 150 unsafe control actions and between 250 to 760 loss scenarios. And again, this was also a very high-level analysis without any details. So when we conduct an in-depth analysis, including every detail of the system, then we will have a very large number of unsafe control actions and loss scenarios. And, one of the most important advantage of STPA is that the method adopts this top-down approach. So we can start from a very simple model like this. And we can refine this model and we can develop details of this model when we have additional information. For instance, inside this master valve module, we have valve actuator and the valve itself. Then we can slightly modify this control diagram like this. The open master valve command is provided to the actuator. And the feedback is also provided from the actuator. And the actuator provides some physical force to open the valve. And the CO2 flows to the valve and to the engine room. So in the same way, we can develop more details inside this CO2 release control system. For instance, the control algorithm or the human-machine interface and the power supply system and so on. So we can include all those details and we can refine this control structure when we have additional information. And this can apply for identifying loss scenarios. So for instance, this loss scenarios is about the physical failure of the valve module. Now we know that there are valve actuator and valve itself inside the valve module. So we can define this loss scenario into two like this. The first one is the failure of the valve actuator. And the second one is that the valve is stuck in a closed position, for instance. And if we have more information inside this valve actuator, for instance, we may have some electrical motor and electric power supply and a small control system, then of course we can define this loss scenario into more details, like failure of the electrical motor or failure of the power supply and so on. So this is how we can start from a very high level and very simple control structure to the very detailed in-depth analysis. So this is a very important advantage of the STPA because we can use this method from the very beginning of a project. So normally, in the early stage of a project, we have a very limited information. But even we have a very limited information, then we can still make a simple diagram like this. And after we have more detailed information, then we can refine this model like this, including more details. And when you have more details, of course, for instance, inside this actuator, then of course we can modify this diagram, including the motors and power supplies and control systems and so on. So this is very important strength of STPA. So this was how to conduct an STPA analysis. And this is your turn now. So we will use a forward collision avoidance system of a car. So you can do some exercise to conduct this STPA. Then let me give you a description of the system first. This is how this collision avoidance system works. So step one is that the car is measuring or sensing the distance from this car and the car in front. And if the car approaches close to the front car, then in step two, the system provides some warning to the driver. And in step three, if the car still approaches too close to the front car, then the system automatically engages the brake. So we can avoid the collision with the front car. And this is a system block diagram of a collision avoidance system. But in our exercise, let's make it simple and let's focus on step three only like this. So if the car approaches too close to the front car, then we will have automatic brake engaged. Then let's say that we have a radar as a sensor and electronic control unit ECU as a controller and brake module as an actuator and the human operator, the driver, as another controller. So use this case and follow these 4 steps and conduct the STPA analysis.